Good morning, ma'am.
Okay, so we were in basic computer organization and design. See, your computer needs an instruction to execute, right? So instruction is stored in the form of sequence of bits, ones and zeros. Okay, your computer has to decode the control unit available inside the computer, has to decode those bits, right? Okay, if the total codes are the total binary bits related to one particular instruction, if I say that as instruction code, it is divided into two parts, right? One is operation code, other is operands or the data on which this above said operation need to perform. Okay, so as for based on the operation, depending on the operation that has to be done on the given operands, we know where you can give operands or the numbers to the computer in many ways. You can specify directly in the instruction, or you can specify it in a memory or with the help of a register, right? After the operation, you can store your output either in the memory or in the registers. Okay, so everything you have to specify in your instruction. That complete set of sequence of bits is called instruction code. As and when the control unit decodes this instruction, it has to initiate several set of control signals or sequence of several other operations it need to initiate, which we call them as micro operations, which helps to complete your given instruction or your given opcode. Okay, so hence whatever is the opcode that we are mentioning, it is said to be a macro operation which initiates several other micro operations. Okay, so the micro operations may be reading a memory, okay, and writing back to memory. See, if an operand is in memory, then you need to read that from the memory, right? Similarly, after the execution, the output, if you want to store it into the memory, you require a memory write operation, right? So to a one instruction to complete, it has to initiate several other small instructions, which we call them as micro operations. Okay. And coming to how the instruction is stored in your memory. So as we mentioned, in the initial stage of, so we are using the basic computer organization, which uses a von Neumann architecture, where common memory is used for storing both program and data. So for a simplicity, assume that memory is of size 4096 words. Okay, so here 4096 into 16, it refers to my memory size is 4096. It means these many number of locations I will be there in my memory. Each could store 16 bits. Each location is capable of storing 16 bits. Okay, right? So 4096 locations are there. Each location is able to store 16 bits. So I can say the number of address lines required for addressing that memory is completely depending on the number of locations. If I say capital N are the number of locations, then the number of address lines required to address these many locations is how many? Can anybody tell me?
11.
11 address lines. How we got this? the number of address lines required are log n base 2. Okay, so you need to appropriate your small n. If I say small n is the number of address lines, this should be n log n base 2, which should be up maximum. Okay, so whatever is the value that we are getting, it should be greater than or equal to. You need to choose an integer value because number of address lines will be an integer. Okay, so which should be greater than or equal to this value. So if you are unable to express this in terms of 2 power n, okay,
ma'am, it is 12, ma'am.
Yes,
it should be 12, ma'am, not 11.
Okay. 2 power n. If the given number of locations, if you are unable to represent in terms of 2 power n perfectly, then I can take the next subsequent integer value as the number of address lines. Okay, so as per given number of locations 4096, which I can express this as a 2 power 12. So number of address lines required to address this any single location is 12 bits. Okay, so 12 bits means your memory locations will start at, if I let us suppose it may be the least location, 12 zeros to 12 ones, where I can represent grouping 4 digits together, 000H2 F. This may be your memory addresses. Okay, so every memory address will have 3 digits or 12 bits. Right, so and each location is now capable of storing 16 bits. So whatever it is, your operand or your instruction code, okay, is should be of length 16 bits. Okay, if I read one memory location, since a common memory, the provided information from one particular location, it can be either instruction code or the operand or the data item. Okay, so that is completely based on which memory location we are reading. The address values will distinguish the instruction code from the data. Okay, so based on the location that we are reading, I will be getting 16-bit information. That can be a binary operand that refers to data. If you are reading memory locations related to data area, it can be an instruction code if you are reading a memory location related to instructions related to a program. Okay, so in your instruction, basically it should be coded in zeros and ones in such a way that it has to give the minimum information to the execution unit or to the CPU, central processing unit. What is the instruction to be executed? Right, it means the op code, which is nothing but operational code short form. Right, what is the operation to be performed and where it has to on what operands it has to perform. Okay, so for this is what we call as stored program organization, where our program is stored initially in your memory and we will read one by one instruction and we'll execute. Okay, so and for stored program organization, basically single register we are using, which we call it as a processor register or accumulator, that holds one of the operand, and the second operand will be specified in your instruction code. Okay, this is the first assumption that they are considering. First operand is in accumulator, and accumulator is the processor register which holds one of the operand as well as the destination also. Okay, result also. Right, so result will not be now stored in the memory, it is stored in register itself, that is accumulator. Okay, so hence you require to specify only a 12-bit information related to the second operand. Okay, so all these 16 bits now they are separated. You require 12 bits minimum for addressing this particular memory area. So remaining 4 bits are dedicated for specifying the opcode. Okay, remaining 4 bits are dedicated for specifying the opcode. In that way, the total 16 bits are separated. Okay, So to address this memory, next we are going with different addressing modes that facilitates writing the program for implementing loops and all. So the given address, whatever it is specified in your instruction, that may refer to direct address or indirect address. Okay. See, indirect address mainly helps for implementing loops. Okay. So we'll see while going for programming. If it is a direct address, whatever is the 12 bits given in your instruction refers to the data item. Indirect address means these 12 bits hold address of an operand which is available in another memory location. Okay. So this is what the operand address, it is available in another memory location and that value is available here. Okay. So this holds 16-bit information. So 16 bits can be held here. Okay. So if you observe, if your memory is larger in size, where your operand existed, right? I can't store the 16-bit information in your instruction format, right? Because only 12 bits are reserved for addressing my memory. If I have a larger size memory, but based on the instruction format, I can able to address only this much memory. If your data operand is beyond this, then this indirect addressing mode helps to address any of the operand beyond which. So that I can have up to 2 power 16 memory access, because 16 bits is able to store in this memory location. 2 power 16 means memory size is being extended to 64. 2 power 10 is 1024. In terms of computer language, we call it as it's kilo. Okay, so it can be extended to 64 kilo, and each location, as I mentioned, it is of 16-bit width, so 64 kilo watts size. With the help of indirect addressing mode, that facility is available. As per the reserved address, which is of just 12 bits, I can access a memory size of just 4 kilowords, 4096. We can refer as 4K. In terms of computer language, it is 4K means 4096. 1K means 1K is nothing but 2 power 10. Okay, so in terms of decimal, if you talk, 1K is 1000, right? But with respect to computer, it is 2 power 10, which is approximated 1024. It is approximated to 1000 and 1K. Okay, so 1K locations means 1024 locations, not 1000. Similarly, 1 mega means, which is 2 power 10, it is 2 power 20 number of locations. Likewise, 1 giga, 1 tera, we will be having. Okay. So this is the advantage of indirect addressing mode. We can extend our memory accessing capability by using indirect addressing mode. And that too, here it is indirect memory. Okay, so memory indirect addressing mode. Okay, it means address of the operand is available in another memory location. Okay, so this is what called indirect memory addressing mode. Okay, right? So this is how indirect memory addressing mode is used. So to distinguish the available 12 bits in your instruction format, whether they are related to, they specify that direct address or indirect address. To distinguish between these two, you require one more bit. Okay, so the most significant bit of your instruction code we are dedicating for distinguishing whether it is indirect or direct address. Okay, so this I bit, if I bit is 0, if I bit is 0, it is direct address. If I bit is 1, it is indirect address. In that way, the classification is happened, so that now in a memory type of memory referenced instruction format. Okay, so here we are referring a memory for the second operand. In this memory instruction format. I can say this as memory reference instruction format, where out of the 4 bits, 1 bit we are separating for addressing the memory, either direct or indirect. Only the available bits for opcode are just 3 bits. So with the help of 3 bits, I can have 2 power 3 number of distinct operations. Okay, so 8 distinct operations I can perform with the help of these 3 bits only. Okay, right? So number of operations that we can perform based with respect to CPU, that completely based on the number of bits that you are dedicating for representing your opcode. Okay, in memory reference type, only 3 bits are available with which I can perform 8 different operations. Okay, so 8 different operations, each require if 2 operand fields. Okay, one operand is in accumulator and other operand is specified in your instruction. Okay, such operations I can perform 8. Okay, this is what called memory reference instruction. Okay, so while we coming for the list of registers, as I mentioned, only the accumulator register is available, which holds one of the operand. So operand is of 16-bit width. If I suppose, then one accumulator is readily available for operation. Okay, so it is not just sufficient this one accumulator. As we have seen, we require a lot more registers for sequential operation. Okay, so for we know our program is stored in your memory, right? As per stored program organization, our program is stored in one particular memory location, right? So we have for our example, we have 4 kilo number of locations, out of which our program size, it may be depending on the number of instructions in your program, it may be 20 byte 20 words or 30 words, whatever it is, it will be stored at somewhere in your memory location. Okay, so from that particular instant, from that particular memory location, you have to start your program execution. Okay, so start of your program will be indicated by a 12-bit address, right? So this 12-bit address have to be given for your processor for start fetching the instruction from your memory. Okay, so whenever we read a program byte, program word, program or instruction from your memory, we call that term as fetch. If you read a data item, then we call that as just memory read. Okay, so if you read a program, we call that as fetching an instruction. Okay, so to fetch the first instruction, it should require an address of your program. For storing that address, I require a program counter, which we call it as a PC. Okay, program counter, right? Some computers it names as instruction counter, whatever it is, both are same. Okay, so program counter, why the name is counter? Because after reading the first instruction, it has to increment automatically to point to the next instruction to be fetched by the processor for execution, right? Okay, so it has to be incremented automatically. So it needs to increment, counting has to be done after fetching one instruction one by one. So hence we call this as a program counter, which should be of width 12-bit, because my memory, I could able to address a memory of 12-bit width. So PC can be limited to 12-bit. And once I fetch the instruction, which is of 16-bit width, because every memory location is of 16-bit width. So the instruction code will be stored in a particular register. It has to be stored in a particular register, from which it has to be given to the decoder circuitry or the control circuitry, which has to decode all the bits. Okay, with the respect to the bits only, the control unit knows what is the operation to be performed, where are the operands, and then after the operation, where the result has to be stored. Everything can be decoded by the decoding circuitry, right? So you need to store the read instruction, which is of 16-bit width in a temporary, in one more register. We call that as instruction register, which is of 16-bit width, right? So IR is of 16-bit width for storing your instruction code. Once you got the instruction code, you need to decode that, right? Okay, so for decode, after decoding, if based on the type of instruction, again, we have talked about only memory reference instruction, right? So based on the type of instruction, see, if my instruction is having only operations like clearing the accumulator contents or complementing the accumulator contents, in that case, I require to perform the operation only on the register, right? Okay, so these we call them as register reference instructions. In case of register reference instruction, I do not need to specify the 12-bit memory address in my instruction. Okay, so only what is the type of operation that you want to perform on the register is sufficient. Whenever I don't require to perform 12-bit memory address, the most significant bit that we have used under memory reference as direct or indirect referring, okay, that is free now. Okay, so now our opcode can be of 12-bit width. Our opcode can be of 4 bits together, I can consider, and I can specify the operation with respect to register. Okay, so I can have a number of operations I can do with now with respect to registers, right? That's what register reference instruction, right? So for that, based on the decoder has to decode the instruction whether it is related to memory reference or register reference. If it is memory reference instructions, the least 12 bits will specify the address of the memory operand, right? And that has to be stored in a register which access the memory. Okay, that's what called address register. So address register is sufficient of 12-bit width which holds the memory address. So once you have the address of the memory location where your data item exists, then you have to perform one more memory read operation, okay, for reading your data available in your memory location, right? The data is again is of 16-bit width. For storing that data, you require a register, that is what called data register. And between the data register and the accumulator, the operation is carried out. If any temporary values you want to store, another temporary register you require, all these are of 16-bit width. Okay, so all the data register, temporary register, accumulator, all are of 16-bit registers which holds the data. So hence they are of 16-bit width register. Okay, sometimes if your datum is coming from an input device, right? If your datum is coming from an input device, you can perform an operation which we call read the input device. Okay, right? So you can read that input device and store that information which we are getting from input device in a buffer. We call that as an input register. So usually we are reserving 8 bits. A character can be read from input device at a time, which can be of 8-bit width. Similarly, output, if you want to send a character to an output device which is of 8-bit width, you require another buffer register, that is what called output buffer register. Okay, so again, if you want to perform operations with the input and output devices, the operations like read input device, right, and then write onto output device, these are only the operations that we can perform with your input or output devices, right? You can't execute directly on data coming from input device unless it is storing into a temporary register, okay, or a buffer register, right? So hence if you are reading an input device or if you are writing onto an output device, you don't require any memory reference. We just require address of the device, input or output device. Okay, so hence again the instruction format can have another type that is referring to IO. Okay, So totally there will be 3 different types of instructions. One referring to memory, we call them as a memory reference instructions, and the second register reference instructions, right? And third one IO reference instructions. Okay, so to have all these operations, we require these many registers. So if you see the number of registers, it is 4 plus 4, 8 registers. Okay, out of which the temporary register is used by your execution unit internally, right? So, and the program counter PC will be incremented every time. Based on one instruction fetched. Okay, so you need to now provide the communication between these registers, of course, along with the memory, because memory is very important location where your program and data is stored. Okay, so if you combine all these registers and memory, see, I have a PC, address register, instruction register, temporary register, and input and output registers, data register, and accumulator register, and of course your memory. Okay, so totally we'll be having 8 registers and 1 memory location, right? So out of now you have to provide these the communication between all these registers, including the memory. Okay, so whenever you want to establish the communication, you have to provide the paths to transfer the information from one register to another or between memory and registers. So there will be a number of wires because see, if you want to transfer a 12-bit information available in IR to the address register, I require 12 lines to be connected here. Okay, and similarly, a data from memory to data register, I require 16 lines have to be connected between your memory and data register, right? Similarly, if you want to read instruction from your memory, 16 lines lines have to be connected between instruction register and your memory. Okay, for accessing the address, I have to connect 12 lines of address register, or for accessing an instruction, 12 lines of a program counter to your memory. So there may be number of wires which will be there for establishing the connection between the registers or between register and memory. Okay, so which becomes to be a clumsy, right? As and when more number of wires existed, system shown as a clumsy, and as well as if any fault occur in a in your output, then recognizing where is the fault is very difficult. Debugging of such connections are very difficult. So a more efficient scheme for transferring information in a system with many registers is using of common bus. Okay, so that's what the common bus system, which uses a certain multiplexers. Okay, so these will multiplexers with selected lines of S0, S1, S2 on all your registers helps to connected by with the help of 16-bit common bus, right, which helps to provide communication between all the registers and memory unit. Okay, see, let us see how the connection is happening. See, outputs of 7 registers and memory are connected to the common bus. Outputs of 7 registers and memories are connected to the common bus. See, one register, which is we have 8 registers, but 7 registers are only connected because we have input register INPR, which is coming from your input device, and it is directly given for ALU for operations. Okay, so this data will not be transferred to any other register. Directly it is given to adder and logic. Okay, so this is what we call ALU, arithmetical and logical unit, right? So where the operation is carried out. Okay, right? So out of all these 7 registers, there is a possibility of transferring the data. So these output from all the 7 registers are connected to the common bus. Okay, we have totally 7 registers which can provide the data for transferring between the registers or memory, and 1 memory unit. So totally 8 devices we have. Okay, so out of which 1 device have to be selected for outputting data onto the common bus. Okay, so which device you want to select, that can be memory or any other register. So to select that one particular device, I require a minimum 3 selected lines, right? So those are called S2, S1 and S0, which are connected to a multiplexer. So based on which I can select any one of the register or memory location for outputting your data onto the common bus, right? See, if you observe these selected lines, if S0, S1, S2, if all the 3 are ones, then the selected is a memory unit. So there is a 7 here. Is it visible?
Yes, ma'am.
Okay, so if all the 3 lines are 1, then it selects a memory unit. So hence it is 7. If the lines are 0, 0, 1, it selects address register, which holds the 12-bit address. If it is 0, 1, 0, it selects a program counter. Okay, so PC is selected 0, 1, 0. And if it is 0, 1, 1, it selects data register. Accumulator is selected, it is 1, 0, 0 and 1, 0, 1. Data, instruction register is selected, and 110, it selects temporary register. Okay, output register, as I mentioned, this will send to output device. Okay, so this won't places anything onto the common bus. So this register and input register will provide data from input device to the ALU. So these 2 registers won't place any data onto the common bus. So hence these 2 are not connected. So remaining 6 registers along with the memory, 7 combinations are used for selecting any one by using the multiplexer 8 to 8 by 1 multiplexer, which is selected by using 3 selector lines S1, S2 and S0, right? See, the lines from the common bus are connected to the inputs of each register and data inputs of memory. See, here we what we want the transfer between your register to any other register, or transfer between a register to your memory. Okay, either of them can happen. So after reading, after placing the data item from a memory or any of the register onto the common bus, right, onto the common bus, this 16-bit information or 12-bit information based on the register that you have selected will be placed onto another register or onto the memory. Okay, right? So hence there will be an input lines also connected to all these registers onto and the memory. Okay, so because all these registers and memories are connected via input lines, and only one particular device has to accept the data available on the common bus. So whichever need to accept the data, that particular register will have a load control input, will be enabled to receive the data available onto the common bus. Am I clear? Right?
Yes,
so
ma'am.
any one of the register or the memory is selected to place data onto the common bus by using the selected lines. So the available data on the common bus will be accepted by any of the register or the memory as and when the corresponding load control signal is active. Okay. So in the next coming clock cycle, the load control signal of the corresponding register will be active. So that particular register only accept the data into it. Otherwise, remaining registers won't update their data item. Okay. Right. So the particular register whose load input is enabled that receives the data from the bus during the next clock transition. Okay. So the clock is very important here because these are the sequential operations. Reading the memory, we call for instruction, memory fetching, decoding, reading the memory for data item, and then executing. So these have to be done in a sequential manner. So the timing is controlled by the clock. Okay. So clock is very important, which is connected to all the registers and the devices available in your bus system. Okay. So for each clock, for the first clock pulse, you have to perform one particular operation. For the second, what is the operation? For third clock pulse, what is the operation? So you may require number of clock pulses to complete the instruction execution. It is not just a single clock pulse, right? So to complete an instruction execution, there are several stages. Each stage requires several clock pulses, right? So you require a number of clock pulses to complete one particular operation, one particular instruction execution. We call that as instruction cycle, that we will see anyway a bit later. Okay. So this is about load control signal. So now memory receives the contents of the bus whenever memory write control signal is activated. Okay. So memory will places the data onto the bus after selecting, not only the selecting, and also it has to provide a read control signal need to be provided for memory. Okay. So memory read and memory write are the control signals for accessing the memory. So memory places its 16-bit output onto the bus when the read input is activated. Memory will accept the 16-bit input available on the bus when a write input is activated. Okay. How load control signals are there for address register or data other registers as read as load write control signal. Similarly, memory have write control signal. Okay. Load for registers. Okay. And memory write control signal is for memory unit. And now coming to the registers, input and output registers. Input register receives a character from input device, which is then transferred to the accumulator. And similarly, output register receives a character and from accumulator and transferred to the output device. Okay. So the transitions are the transfer of data is happened between the accumulator and either input or output device only. Okay. There is no transfer from output register to any of the other register except with the accumulator. Okay. So accumulator is the processor register which involves for accessing either input device or output device. So input register will whatever is the value in input that will be loaded onto the accumulator. Okay. Or the value coming from a data register and that will be updated onto the accumulator after the operation. Okay. Or the accumulator itself after the operation, you will be having the result available in the accumulator. That itself may be loaded directly onto the accumulator. Okay. So accumulator is loaded with n number of possibilities. One possibility is the direct so data register directly onto the accumulator, or else data coming from input device, or else the same accumulator contents updated back to the accumulator. So this can be done if sometimes you want to increment the contents of accumulator or decrement, that can be done by one more control signal apart from load, that is what called INR. INR means increment. Because for program counter, you require a control register which has to be incremented for pointing to the next memory address for fetching. Similarly, address register, similarly a data register, okay, and accumulator register. So they require another control signal which is called INR for incrementing its contents, for facilitating a smooth program sequence. The 16 lines of Commonbus receives information from 6 registers and the memory unit, and the bus lines are connected to inputs of 6 registers and the memory unit. 5 registers have 3 control inputs: load, increment, and clear. You may require to clear the registers sometimes, so clear another control signal. And this type of register is equivalent to a binary counter with a parallel load and synchronous clear. Okay, so these registers, we call them as a binary counter because there is a possibility of incrementing itself with the help of INR control signal. And with respect to the clock, there is a possibility for clearing its contents automatically whenever we require. Okay, so hence we call it as a parallel load and synchronous clear. Parallel load means all the 16 bits available on the common bus will be loaded at a time onto the register. Okay, right? So let us have define these 3 control inputs. Summarize. The 16 inputs of accumulator come from the add and logic circuit, right? So which performs the operation on DR and AC, and the result will be loaded onto AC. So as I mentioned, it has the 3 set of inputs. One set of 16-bit inputs come from the output of accumulator, and they are used for implementing register micro operations such as complementing accumulator, shifting the accumulator, clearing the contents, increment the accumulator. These are register reference type of operations. And another set of 16 bits come from the data register, which has to perform several operations, addition or subtraction or logic operations like AND or. Okay, so between accumulator and address register, such operations can be performed. Okay, so we have a facility for extra bit that occurred during the operation, that is what called E bit, extended accumulator bit, which holds the carry or borrow depending on the type of operation, maybe addition or subtraction. And the third set of 8-bit inputs which are coming from the input register when your operand is available in an input device, that is input read. Okay, so accumulator can have another set of data item coming from the register. Okay, so as I mentioned earlier, this is what the complete common bus, how the bus, your common bus consisting of 16 set of lines, and the data, it allows accepting or placing data from these 6 registers along with the memory by selecting one particular register or the memory address with the help of the selector lines. And the data available onto the common bus can be loaded onto any of the register, or it can be written onto the memory unit based on the corresponding active control signal is received. Either it can be a load or it can be a write, by which you can facilitate the communication between these n number of registers along with the memory unit. Okay, so this is the common bus system. And Now, we have already seen the three different types of instructions that I have explained earlier. Computer instructions. So the basic computer has now three instruction code formats depending on the type of reference. Okay, so basic computer instruction, if you are referring a memory, then the 16 bits, out of the 16 bits, 12 bits, least 12 bits are for address, and most significant bit will specify whether this address is a direct or indirect address, and remaining 3 bits only used for specifying the operation, which we call as operational code, right? This is what called memory reference. And next, if the operation is on direct with the accumulator, then you don't require any 12 bits for referring the memory. Okay, so these 12 bits are now free. These 12 bits are now free. Okay, so I'm using now these 12 bits to specify what is the operation to be performed on my register accumulator. Okay, because to distinguish it from a memory reference and other either register reference or IO reference, the opcode, which is having 8 different combinations, the 7 different combinations are used for specifying the memory reference instruction, and one combination which is all ones. If this bit is all ones, I can conclude that the instruction is either register reference or IO reference. Okay, IO instruction type. Again, based on the most significant bit, I can decide whether it is register reference or input output instruction type. Okay, so this is how the control unit or the decoder unit inside your CPU decodes the instruction. Okay, so based on these 3 bits, the decoder decodes whether it is memory reference type or register or IO reference type. Okay, and after these 12 bits, these are used for specifying the register operation, and similarly the IO operation here. Okay, so your arithmetical or logical operation, whatever you want to do, which requires 2 operands, one operand is there in accumulator, other operand should be there in memory. Okay, if it is in memory, and any arithmetical or logical operation that you can implement a maximum of 7 here, 0, 0 to 1, 1, 0, which is 6. So 7 distinct operations you can perform with this length of your instruction, which is 16, and by memory reference is of 4 kilobytes. Okay, for register reference, we have a 12 bits available for specifying the register operation. Whichever are enough, that many you can refer. Similarly, 12 bits are available to specify the IO operation. Whichever is required, you can specify that. So possible combinations, we have 2 power 12, but out of which only that many operations we can't do on input or output device, similarly on a single register. Okay, so this is these are the 3 different type of instruction formats: memory reference, register reference, and IO reference. So by which, how many types of instructions that I can include? What are all the instructions? Okay, so you need to select the instructions in a proper way, so that while implementing your program, you should not be in a tight spot that this instruction is not there in memory, I can't implement this. Likewise, okay, so you need to now assume, or you need to design your hardware now for a particular set of instructions. Okay, see, with this we have concluded that the available instruction formats and how many opcodes I can implement. Okay, now what exactly the opcodes are, what exactly the instructions I can implement will be decided in a later version. Okay, so these are the list of instructions that a basic computer initially they have used. Okay, basic computer instruction. As I mentioned, I have a facility for 7 different operations with the memory reference type. Okay, So if I is equal to 0, the 12-bit address that we have specified, it is direct address. If I is equal to 1, the 12 bits are referring to indirect. Okay. And coming to the operation, if it is 0, 0, 0, so the most significant digit. Okay. See, upper 4 bits. If I is equal to 0, next 3 bits decides the opcode, right? If it is 0, 0, 0, it refers to AND operation. We are performing logical AND operation with a memory word whose address is available in these 12 bits. And between that word and your accumulator, a logical AND operation is performed and the result is stored back to accumulator. That is what the operation. Okay. If these 12 bits, whatever you are referring, if they belongs to indirect address, then I bit will be 1 and the opcode is same 0, 0, 0. Okay. So then the upper 4 digits are said to be 8. Okay. So opcode for a particular operation is the same, which is 0, 0, 0. Either it is AND or any other thing. Okay. 0, 0, 0 refers to AND operation. If I is equal to 0, these 12 bits refer to direct address. If it is I equal to 1, these 12 bits refer to indirect address. Okay. And the operation is AND with the memory word to the accumulator and result stored back to accumulator. Okay. Similarly, add operation. Add operation is given for 0, 0, 1. Okay. So I have dedicated 0, 0, 1 for add operation. Okay, if I equal to 0, this will be 1. If I equal to 1, this will be 9. And next, load accumulator. Load accumulator means whatever is the data item available in this memory address that we are loading onto the accumulator. Transfer from memory to accumulator. It is nothing. Okay. Similarly, store accumulator. For load accumulator, you have dedicated 0, 1, 0. For store accumulator, it is 3. So 0, 1, 1 is the opcode for store accumulator. Right? See, all these are operations. Sometimes you may require to perform loops or jump from one location to another location. So your instruction should include such type of instructions also. Okay. So hence we have given branch, unconditional, branch, and a save a return address. The difference between these two, branch unconditional means we are branching to a specified address which is available in the remaining 12 bits. Branch and save return address. See, branch unconditionally means it will go to a specified address and it will execute from there. It won't come back to the location where the branch is called. Okay. So, but branch and save return address means this is used for calling a functions. Sometimes if you have a repeated set of instructions need to be executed, we'll implement in the form of functions, right? So after executing that set of instruction, again, the control has to come back to the specified location. So the return address have to be saved somewhere. For that, BSA is used, branch and save return address. This is similar to calling a function. This is similar to implementing a jump. Okay. And then increment and skip if 0. So this is another control transfer instruction. Okay. So these are memory reference type instructions which are dedicated for this 100, 101 and 110 for these 7 types. Okay. So similarly, we have register reference and IO reference. So that we'll see in the next class. Is there any doubts?
No.
Okay, let me take the attendance. And that division algorithm is got ma. Only the thing that I forgot. I mean, I haven't explained you is a division restoring algorithm is meant for 2's complement data. Okay, you have to take 2's complement data and perform the operation. We will explain that in the next classes. Okay, so
Yes, ma'am.
Let me take the attendance. (62) absent. (79) absent. 86 absent. 90 absent. 96 absent. 101. 108. 110. 113. 115. 120. Absent. Okay. Okay, ma. Thank you. Bye for today.
Thank you, ma'am.
I'm 90 present, ma'am.
90 present. Late Mari.
100 present, ma'am.
100% only, but 90 is not there here. How joined?
No, ma'am. My name was in the last.
That's why I asked you to rename roll number followed by name, so that it will be easy for me to take the attendance. Okay, ma. Thank you. I'll put that present for 90. Bye.